start recording. Okay, so let's see where we left off. We just got the circle thing working, and hopefully that works on yours as well. And we're finding collisions between circles. So let's see. Last time I drew this funky diagram, and it was like, here's a circle, and here's a circle. And what we can do is we can find an axis, or we can find I guess this is also an axis, but we can find an axis between them that separates them. And if we can find that, we know that they're not touching. But we can also project them onto this axis, like so. So we can say, here's two circles that are touching. Let's redraw that. Here's two circles that are touching, and we can again draw an axis between them. And obviously, this is the only useful axis. Like, we could draw like this axis between them or something, but that is not so useful because, for example, if we drew this axis between them, they're colliding on that axis. But I guess I've jumped ahead a bit. So this one covers this section of that particular axis. And this one covers this section. And so we can look at the overlap between them and say, you know, they're intersecting, and we know how much they're intersecting by. They're intersecting by this much.
Right.
And we know that that's the only useful axis, because if we did this, we put an axis there, we can like project that one. Project this one down onto this axis, and if we project this one up onto this axis, sort of, we get like an overlap, but you know, it's like a false overlap. It's not a useful axis to compare them on. So the theory goes that if you test every axis, like if you have any that they don't collide on, then they don't collide. But you can be smart and be like, well, there's actually a limited number of axes that are actually useful. And in the case of two circles, it's obviously just the axis that runs between the two center points. So today we're basically going to be making this diagram and talking about how that works. So let's head over to the code. And yeah, do you have, so for people watching at home, this will be up at some point as well for download, but I've made this happy little diagram. Have you got this up on like another monitor or something?
No, I'm just gonna bring it up on my phone, so
okay.
At least I'll have.
Yeah, so this is just handy. Like, this is all stuff that we've covered and that you need to have memorized, but this is all of the vector maths that we'll need for today, basically. So that's handy to have. Okay, so we have to start with a little bit of housekeeping, just to clean up stuff. So let's just nuke all of our commented out stuff. I think, in fact, it looks like you may have already nuked it. Like all of
yeah, that
stuff.
was just me comparing the when
yeah.
I didn't understand why distance squared was more efficient until we looked at it.
Oh yeah, no, we went over that. Yeah. Yeah, so I just got rid of all the line drawing stuff. Now, if we look at zoom amount and like find all references on it, we can see that we're doing this a lot. It's like calling zoom amount, zoom level. So, and we're going to be doing that a whole lot more because we're going to be doing this trick a lot. Because we're drawing like overlays and we want them at screen resolution, not world resolution. So we're going to do this trick a whole bunch. So we may as well make this a thing. So float zoom get return zoom amount zoom level. That's just going to make our code a little bit clearer. And then we can go through and replace at least this one, so we don't have all that cruft in our drawing code. That's item 2. Item 3 on the cleanup list. So this is sort of getting into some actual stuff, and that is we are going to want to draw some lines, some arrows. And why we need to do this will become apparent fairly swiftly, because when we have, say, 2 circles that intersect, we're just indicating that they're intersecting with this line, but we're actually going to want to point out direction. We're going to be like, well, we want to know which one is the start and which one is the end. So we're going to want to replace this line with an arrow. Obviously, I'm just like, that won't run because that's not a method yet. So we're going to need to make this method. And this should be fairly straightforward. I think, have we even done this before at some point? Possibly.
No, that was bonus homework. That I never did.
That's fine.
I am a bad student.
So let's just bang together this thing, and so I'm gonna. I'm in line batch, by the way. Seeing as we have this nice class for, we have this circle method, for example, we can add an arrow method.
You're going to use perpendicular math stuff, right?
Yes, so I'm going to hand this over to you.
Ha, no you're not.
I totally am.
Okay.
I'm going to watch you code for a bit. I'm going to draw a diagram that might be helpful.
What was the last, it was color for arrow after that? Arrow
head size, radius, color.
FML. 2 lines. And we're closing it probably, so it's 3 lines. And then, yeah, okay, I'll start there. So have to fill in all the FMLs. Okay. Well, hold on. This shouldn't be the end of the world. So I know I know where my line is. I don't have to draw the line itself. I'm assuming I'm gonna let a different. No, I'll do it in here. Yeah, exactly. I'll just do the line. I don't have thickness though. I'm not arbitrating that.
Oh, sorry. I said radius. I meant thickness. That's my error.
Right. No. Well, yeah. Radius is no. Anyway.
And sort of API design-wise, we might want to think about whether we want to take thickness and radius and sort of make them the same thing, because we've got radius for the circle but thickness for the lines, and it's like, well,
yeah, they're the same thing because we have the nice little circle end caps anyway, so radius is probably the
So that's the thing to think about. Perhaps what do we actually want to do with that? So I've drawn a pretty little diagram, and
yeah. Right. So, yeah. Okay. So hold on. So I need the perpendicular of the end. We did some methods for that. I think perp. So I'm gonna go perp 270.
So I'm gonna show you something interesting. So I'm gonna draw this in red. So you keep coding, and I'm gonna try and draw what you're doing. So if this is the world origin, end is this vector here.
Right.
So if we took the perp of it, you'd get this vector here, which I'm not sure is meaningful. Sorry, in fact, you'd get the vector of exactly the same length. So it would be like that vector here.
Right. Pooh. Well, I want a unit vector, I think. Right, I gotta normalize it anyway.
So you do have to normalize something. So,
okay.
what you are looking for is the sort of thing we call a basis vector.
Yeah, I remember that from the 3 brown, 1 blue. Sort of. I mean, he said it. That's what I remember.
So if this orange is no good, let's try green. If this is our x and our y basis vector for world space, we kind of want this blue one, which is like a basis vector that's stuck at the end of this line and is the right size.
That's right. That's what I need. So in order to get that, well, could I? Well, I can use subtraction, can I?
Yep.
With the translation to get the angle-y bit, and that would just be wouldn't that be something like the perpendicular of the
take it one step at a time.
Well, I've got this. I mean, the end position isn't like it's what I really want is to take the. I want to capture the start vector and then just add don't want to add the start and the end together, right? To get to the end.
Take a look at the cheat sheet that you have up.
Yeah. Okay. Yeah.
Because the first diagram on here is pretty much what we want.
That's right. Yep. I want. I want to get. Well, they're both B. One of them. Oh yeah, no. B is over there. And I want. So if start is A, I'm looking for. Yeah, I'm looking for the perp of start. Am I not? I don't know why I keep going back to. I want the perpendicular of that.
Well, perpendicular gets you like an angle that's 90 degrees. So if we're trying to get, like, I'll zoom in on this. Here's two vectors that are perpendicular.
That's right, but why wouldn't I get the perpendicular of the start end vector and then add the start to slide it over to the end and then normalize it? That's what I'm trying.
Well, you can do that. That's definitely a thing you can do. But what I'm going to say is, before we try and head out in this direction, like the perpendicular direction, let's try and head out in the normal direction first. So we'll try for this one. And once you have this one figured out, then try and get the perpendicular, because that will make...
Oh, yeah, that'll make it easier.
That'll make life a lot easier.
Right, so all I want is the normal is it the normal of A and B, and A is start and B is end, right?
Not quite. There's actual text here that might help.
To find the vector between 2 points, subtract the end from the start. Okay, well, okay, duh. Yeah, sure. Okay, the normal of end minus start. So the opposite of what I said.
Yes. So that should get us. Yeah. So if C is the end and A is the start, we get the vector B. So it's actually this vector here, but you can overlay it onto that. So that's a good start. So what you have now is the vector. Let's see. I was drawing along with you.
Yeah, I want to end minus start, and then I want the perp of end minus start. I don't really want to calculate that twice, but who cares right now?
My diagram is a bit skewed.
No, hold on. Yeah. Oh, woo. Okay, first, put one of these FMLs up here because I want to. This is visualizing it. This is This is not right yet. I have to normalize some stuff first. I'm just gonna make an N, and that's gonna be the and gonna start normalize. Huh. Oh, this isn't one of those functions. It's a void.
That's a static function on vector 2.
Oh, that'll be easier to use then.
Although we could take a little detour. Let's just bang this in. Go to line batch and grab out safe normalize and stick it in vector extensions because we're going to want this a whole lot. Because it's almost never the case that you want to get like not a number out of your normalization.
Right.
So yeah, that's looking good. So public, yeah. So we can head back to line batch and fix up this one instance where we're using it.
Oh,
figure out why it's not there. And then we can use it down here.
Yeah, I just didn't. That's it. All right. So, where was I doing? I want to do this. So I want to do end normal start, safe normalize. That's gonna give me the guy on the bottom, and then I want the perpendicular of that.
So n minus start safe normalize. That actually gives you this guy here. More or
yeah,
less.
the green one, right?
Yep.
And then from there, I just need to perp 270 to get the blue one.
Yep. So we've got our basis vectors now.
Right. I'll call them A and B because that's what I feel like doing.
Sure.
And
sense.
then yes. So first we drew the line. Then we need to draw. Let's say the. Oh. Now I need to. Well, okay, that's all I got. I don't have enough yet.
Okay. Well, we have those vectors. We can use those as basis vectors. So if we want to draw an arrowhead, that's this here. So this thing and then this thing.
Yeah.
So just using
this rotation.
So well, what we want to do effectively is if we're in world space, we want to draw the line that goes there and there. And what we're doing is we're using the basis vectors to reconstruct this shape here on the end of this here.
Yeah.
So this is like a fixed shape. What we're kind of doing is think back to our transformation matrix, how that was made up of two basis vectors, and it's like I want this much of the this much of the x-axis and this much of the y-axis, and now I realize I've actually drawn that incorrectly. It should be redraw that. You know, I want so much of the x-axis and I want so much of the y-axis. So I'm basically recreating this shape. So one thing you could think about is like, okay, if I want to draw that shape, that's like going back, you know, some units on x and some units on y, and then some negative units on y and back on x. So it's like negative n and n, where n is like our head size for the arrowhead.
Ah, yeah, okay.
So that's the shape there, but what we need to do is we need to stick it on the end there. So that's like the question is, how do we do that?
Hello?
Yeah.
Sorry.
That's the question for you. That's your question.
Yeah, but all I got was robot voice, so I don't know what the question.
Oh, okay. Yeah, no. Okay. So we know how to do this. We go back negative n on the x-axis, and we go up n and down negative n on the y-axis, and so that gives us 1, 2, 3 points that we can make an arrowhead out of. Now all we need to do is take this and rotate and translate it up here. Now we have our basis vectors and we have our position. It's just the end position. So we want to move the origin to the end and we want to use the basis vectors to reconstruct it. So it should just be sort of straight through coding with like basically how would you use the basis vectors to make this?
Well,
so the floor is yours.
Doesn't have the cheat sheet doesn't have well, yeah, it was more robot. I'll do my best. The cheat sheet doesn't have translation or rotation in it, but I don't think we need them for this, right? Because if I have the head size, that gives me an X and a Y, and I have I gotta make 2 additional points, right? So you said, on the X it's negative n, and on the Y plus n, and then X on the negative n and negative n. Wait, yeah. I mean, I barely remember this, but am I not just going to, we have a transform for this somewhere? Transform 2D?
So you could spin up an entire transform 2D instance, but that's probably a little bit of overkill. But you do have more or less the right idea there. Actually, you've
I just remember I just remember barely this kind of concept here.
So take a look at the second diagram on our cheat sheet. This is sort of what we're doing to a certain extent when we're
scaling by negative n and n, and then again by negative n and negative n. Scaling,
pretty much. So we're doing some vector scaling and some vector addition. This is all this is.
Yeah, it should be. This should be. I don't know why I lose this so quickly from my brain, but yeah, I mean, there's bits and pieces. Okay, so, why don't we just say, oh, let's F head. We'll float head size. So we have 2 positions, A and B. So A. So okay, I don't know. Arrow. I don't. Names are hard. X is equal to A. Is a vector. So I don't know what I'm doing anymore. But A vector. So how about AX? X minus head size. Y plus size. And then we haven't done any scaling here. This is just you have to multiply this by.
Okay, so let's see what you've done. AX...
All I've done was add it. No, this isn't anything. All I did was add head size to A.
So you're still in world space here is basically the thing. So AX is the normal. So back on our world space coordinates, the normal goes in the direction of the line. So that's unit length 1. And you've basically added head size you subtracted head size and added head size. So subtracted head size from X. So you've gone that way on X, and then you've added head size on Y, so you've gone that way on Y. So you've basically created a vector out here with that first line. So I'm not sure that's going to be correct.
Yeah. No. Well, not at all. I guess. I don't know. Yeah. Don't.
So the key point with basis vectors, if you recall, is the relationship between these 2 coordinate systems. So when we're working over here, you might remember, if we want to draw our head, for example, we'll just have it, unit length for now. In fact, we just want to draw, that top bit of the head. That is what? It's negative. Oh God, I've put my things back to front. Y and x hat. So it's negative, that much x, and it's positive that much y. And so if we want to move it over here, we need negative that much of the norm and positive that much of the perp. So you see how that works? We've taken the x and we're making negative normal down to there. And we're taking the y and we're going up that much on the perpendicular axis. So what you can do is you can scale those basis vectors to create a new coordinate system, is basically what I'm saying.
So, yeah, okay, but if in A and B or X hat and Y hat, I gotta multiply or scaling. So multiplying them by
A and B, yeah, exactly. So A and B
are the perp and the normal. Wait,
yeah. So this in your code, this is A, and that is B.
Oh, for some reason I thought I was making them into the basis vectors.
Well, no, those are the basis vectors.
Okay, so sorry, I thought Y hat meant basis Y.
Well, this is like the world space Y hat. So this is the basis vector for like just the world space. If that makes sense.
Right. Well, I mean, how am I not in world space because I haven't done the zoomy bit?
No, so this is why I've drawn two coordinate systems. We'll come back to this diagram here. This is like the world. This is 0, 0. This is the origin of the world.
Yeah.
And we're trying to move this shape from the origin up into like this thing that's like rotated and stuck on the end of the arrow. So we've got the I call it the world space, but like the neutral space, the
theoretical place where we do our linear algebra, where everything is 0, 0.
Yeah, it's just the 0, 0 space, standard space, and then we've got this translated space up here that we're trying to create. So we need to and rotate.
Yeah, I got nothing. Maybe I shouldn't have had 4 hours sleep, but probably most of it is just forgetting.
Well, that's all right. So
crucial little nugget.
Let's just finish it off. So we've got this A. What we need, we're going out. What do we call it? We call it head size. Let's call that. I've called that N over there, but that's a bad idea. Let's call it H. It's now H for head size.
Okay, I missed maybe 90% of what you just said, but
oh, okay. Quality internet. It will be better in like a month or two, I think. So we've changed N to H just because we've got a normal over here. So H is our head size. So we're going negative H times X over here, and up here we're going H times Y hat. So which is the same thing as saying we're constructing a vector that's like, negative H, comma H, which is very similar to what you've got over here in this first line. It's like that's what we want in like world space or model space or the neutral space or whatever you want. But we want to take that and then we want to move it into this coordinate system. So all we do is we take this value here, which is negative H, and replace the basis vector. So we've got negative H times N hat, and then for this side we've got H times P hat. So we've got what does that give us? This first one is this vector here, and the second one, I'll draw it in blue, is this vector here. And all we do is we add those together. So we're sticking that on that, and we get this green vector out here.
Rick.
So now we have that green vector out here. That's like that vector here. We just, to get the position of it, we just add that onto end. So we've already got end, and we add that, then that gives us, this vector here that we can pass into our line function. Okay? Did you follow all that?
Yeah, except at the end. But
that's all right.
fine.
Let's start by getting this green vector here. Hey?
Yeah, I just want to draw that. So hold on a minute. Yeah. So I thought that's what I was kind of already doing with the vector thingy, but yeah, not exactly. So negative h times n hat.
That's your A.
Yeah. That's because that's the one that's the normal. So I'm just gonna call it n, and I'm gonna call this one p. Not. So yeah, so negative h times n. H is head size times n. What is this? This I gotta do it by. This is a vector.
So this is that red vector here. So you've created this red vector. So it's not a scalar. So you don't need the constructor.
Sorry, I didn't hear anything that you just said.
That's no good. So you won't need the vector constructor because you've already got a vector. Because
right. So I guess,
n is a vector.
Right. So n x. Oh. What? No. What?
No. You don't need to dive into the thing. You were actually good before. You actually were on the right track, but then you started doing which you don't want.
I'm just worried about the I don't know. I don't understand this because it's a vector. I gotta do that.
No. So what you want is take out the dot x is what you want.
Right. Well, I was having problems with that before. Negative h times.
Yeah. So negative head size times norm will give you this vector here.
Yeah.
And then
so what?
Positive h times p will give you this vector here. So we want this green vector here. So all we have to do is add those two together. Exactly. So that's the bit in the brackets, and then ultimately we want to add it to the end to translate it. So that is one of the points of our line. So you've just created this point here. So just store that one away.
Draw that from end to
end plus blah blah blah. Yep.
Galifianakis, and then oh, okay. So why don't I just drop this guy in here and drop this guy in here and forget the...
Well, yeah, now you can do that. So it's sounding like we're on the right track, so I'm going to catch up.
We just draw this thing.
Sorry?
Maybe we should just draw what we have.
If you like, absolutely. So where were we at? Physics game. So I just changed this line batch thing to an arrow, and I need to add in head size like 10f divided by zoom. So this is where we intersect two circles. So this is a quick way to do that. Okay, so let's see what happens when we run this. So we'll need 2 intersecting circles, and it draws nothing. Oh, yours draws something.
Yeah, it's broken as I'll get out, but...
Actually, I know why mine draws nothing, because I actually have no code in there. I'm like...
Oh, yeah.
Still catching up. I'm like, why is it drawing nothing?
Okay. So... Trying a bunch of... This is like... This just reminds me of something. I'll tell you what it reminds me of later.
Okay.
But where everything is in the corner, and it's just a bunch of triangles.
Yes.
But anyway, yeah. So it's inside joke. Yeah, but so I did something silly, obviously here. Oh, is it just because I have this? This is the garbage line at the end here.
That one's the garbage line,
yeah.
so we don't need that.
We don't need that at all.
What are we doing? We end plus.
Hold on, it's still garbage.
I don't know. Yeah. So okay, you can see you're subtracting from 0 here, so you can see that all of your arrowheads are around 0, 0. You actually want them to appear around the end. So you've missed the. Actually, no. Yeah, you've missed the translation step on half of your arrowhead. So just stick an end in there.
Oh, yeah, right, of course. Yeah, right. I forgot. Yeah, the line method isn't continue from here a certain number of units. It's
absolute, not relative. Exactly.
Right.
So if we try that, hey, it's like half an arrow.
Yay.
Okay, so all we have to do now is finish that off. So based on what you know, you should be able to...
Based on what I was given, I should be able to... well, okay, well, the other one was minus n to n, so this one should be minus n to minus n.
Sounds pretty good to me. Let's give it a go.
N minus size, minus head size, and then this one's minus head size. Why not? I don't know. There you go. It's like one symbol different, so... Yay!
So it's important that you understand what that's doing. So how do you feel?
That might take me longer than
that's all right.
Today's session. Well, okay. Well, when you say now I've got this fancy escape button, what do you mean in terms of what is it doing from the maths point of view, or why the arrow is drawing?
Well,
the way
why we did that the way we did it, like basically what a basis vector is and how you use them.
Well, I mean, because of the fact that you had to beat it over my head, I know that it's, you wanted to translate between 2 coordinate systems. I still don't quite. I mean, I get. Like when I look at this, I don't see how we made an arrowhead. Other than, I'm gonna do something silly here. Just hold on, just so that I can see it. So, or like n is like or head size is how much to draw, like how big the arrowhead is, but I don't see in my, I don't see the 45-degree angle that.
Okay, these are on. Let me try a couple of code things. So let me just see if this will work. I think it will. So what I'm going to do is I'm going to grab this line. We're going to build this up in the other direction. So we're going to just start from vector 2.0. So we're sticking a thing at world 0. And we want to draw an arrowhead. So new vector, can't autocomplete while doing that. New vector 2, doobly-doo. Okay, and we want it to be like 10, 10. So I'm just going to use the number, in fact, I'll use the number 16 to be our head size. And so what do we want? We decided it was negative on both of the x and negative on one of the y. So if I run that now and everything works. In theory, if I draw a thing so it appears, I can see it in the... I'm just gonna... I need a new mouse. My mouse has decided to break, so I'm just gonna move our this off right button to middle button, so I can actually scroll the screen around. So make a thing, and so you can see up in the corner we've got this. So this is the point 0. This is the origin of the world.
Yeah.
And we've got an arrowhead coming off it.
Oh, right. Okay. The 45-degree angle is just the Cartesian coordinate because I'm always taking one step back and then one step forward or back.
Exactly.
So on the y. So there's this is simpler than.
Okay.
I get it.
Let's break this down some more. Let's go back into line batch now. Let's split this construction up. So we've got -16, 16. I'm gonna change this. I'm gonna do -16 times vector2 dot unit x, 16 times vector2 dot unit y. And so, sorry, not comma, add. So I'm adding those two together. Now, hopefully it makes sense that this is the same as that.
It's the same.
Note that I've just copied that and got rid of the minus here. Just to keep.
Components 1, 0. Yeah. So unit x, unit y. 1 and 0, and then 0 and 1.
Okay, so let's run this sucker in the debugger.
Yeah, you're adding the. Go ahead.
Run it in the debugger, and it will tell you exactly what's going on. So we've got unit x 1 0, unit y 0 1. We're multiplying it by 16 and -16. So we get this vector -16 16. This is exactly the same as just constructing it straight up as a single vector. Okay?
Yeah, of course.
So we've split it up. Simple as that. And if we run it, and we should have up in the top corner, we've still got exactly the same shape.
Right.
Now, if I wanted to rotate this a bit, I can take our x and change what the x is. So I've got, instead of using this unit length vector on the x-axis, I can use a unit length vector, or frankly any vector, and call that my new x-axis. This is my basis vectors. So I'm going to use n there, and I'm going to use p, which is pretty simple. So I'm going to change that now, and I'm going to do the same thing with the second part. So this is the same as it was before, but instead of using unit x and unit y, I'm using n and p as my unit x and my unit y. Okay, so I'm going to run this sucker, draw some circles so I get that line. Obviously there's no line there, but if I scroll myself over into this corner, you might want to just have 2 circles just to make this a little more obvious. But you can see that they're at the correct angle. So, and in fact this becomes even more obvious if I actually put back this one. So I've got my line here, and you can see that this arrowhead is not necessarily in the right position, but it's at the correct angle. Making sense?
Yeah.
And then all I have to do, now I have my arrowhead, I've changed the basis vectors, so I've done that. So instead of unit x, I'm using unit y, I'm using that. All I need to do now is translate it. So, and to translate it, I just add where I want it to be. So I'm going to add plus end, because I've got 4 points here, and 2 of them are the same, but I add end onto that. And then all of a sudden my arrowhead moves to where it should be. So the addition does the translation, and the change of basis vector does a rotation or a scale or a shear or something, but we're not actually doing that at the moment. Now all we have to do to finish this out, I mean, it's pretty much finished, but we obviously 0 plus something is the same as saying just the thing on its own. So we can just get rid of that, and we're done. And obviously these are now, rather than just 16, we'll let the user specify it.
Yeah.
And that should be exactly the code you have there, yes.
I just
Yes.
I just felt I guess taking it on like I'm trying to visualize arrows in space, and I was thinking things like angles and rotation, and I wasn't thinking at all about this very simple, like it's a step, it's a stepwise kind of algorithm there, just minus n to n, and the arrowhead. I mean that's probably a standard way to do it, right? The 45-degree angle from the point, based on the direction. But obviously, we could make this all angly at some point too, right? And just say how long the angle is if we were making a fancy.
Well, why don't we do that? But rather than doing it in world space, we have this way of doing it. Rather than doing it directly, we have this way of doing it on basis vectors. But there's no reason we can't change the sort of the x and the y values here, because remember we have a vector that's like vector 2. It was called like bar or something. Bar equals new vector 2. We had like 16, 16, or neg 16, neg 16. Yeah. So so because we put in head size, it would be like negative head size and head size. That's our bar. There's no reason we couldn't do something like, and I'm just thinking about how this would work. We're going to need 2 of these. We're going to need top and bottom. So, sorry, that's plus and that one's minus, yeah. So there's no reason that we can't take that and go top.x and top.y x and bottom.y. So that's exactly the same numerically, but we've split these vectors out. So now we're really treating them as basis vectors and making a mistake. We've moved the negative. So.
Oh, right, so they always have to add now.
Yeah, so that's the tricky thing about negative numbers.
Whoa, hee hee.
Yeah.
Yeah. That's I kind of like that better. But
well, it may be useful to actually do that or something like that at some point, because we need to be able to indicate the beginning and the end of a line. When we draw it into space, because that's going to come in really handy. So yeah, all of the negative symbols.
Oh yeah,
because we've moved all of the negatives up into our data.
Derp.
Okay.
Love getting beaten over the head by things I should know already.
Well, that's all right. I mean, it's stuff you need to know. Like this is quite important, and so this is why we're doing this bit first, is because you need to internalize the way that the basis vectors work. So now we're using these vectors as results for this. So, but what if, for example, we wanted to put an angle in there? So, how do we get an angle? And I was going to add this to the cheat sheet at some point, but we haven't yet. So you will recall our funky little guy, the unit circle.
Sort of. Interesting question all on its own. Why did I forget all this stuff? Because we did this for months. Or whatever.
So if we inscribe a triangle in here, so we've got the angle theta. This is a very tiny unit. So am I zoomed 100%? No. That probably explains it. So you have this angle theta in there, and we know that, let's have a bit of color. This one here is sine theta, and this one is cos theta. And we know that that's like, okay, we've got a unit circle. This is like our y-axis and our x-axis. So sine theta equals y, and cos theta equals x. So that's the amount we have to go out on each axis to get an angle. Okay?
Right.
So we want to construct, say, let's make like a nice pointy arrowhead, like that, and we want it to be, we want the length to be, well, this gives us, radius equals 1, so we can scale it up to the head size later. So we just want to get these positions. So that angle is approximately, how big would you say that is? That would be like, that's 90, that's 180. We'll call that like I don't want to say 135 because that's 45 degrees. So let's say 150. And we'll call that one the opposite. So that would be, actually what I should do is I should be like 180 is this, minus 30 is 150, and plus 30 is 210. Okay, degrees. So we want to construct these as our points. So let's head back here.
I've made a terrible mistake.
Yeah, welcome to maths. You mentioned.
Well, I extended the like I was like, oh, this is a good place. We've I'm not too completely embarrassed, but then now we're doing angles. That's fine. We can do it.
So we can do
it's
it.
Almost, yeah.
We know that we've got cos theta is the x-axis and sine theta is the y-axis, and we're going to go, so var cos equals math.cos, actually I'm going to say that's float. So this is going to be cos, and that's going to be theta. Yeah, I'm just going to do the top one, and then we'll reflect it for the bottom one rather than angling it. So what did I say? That was 150. Math helper dot, is it 2 radians, 150 degrees. That's our cosine. And our sine is that. So cosine is the x-axis, so that's cos and sine times head size, and we're just going to reflect the top for this, so we go top dot x and top dot negative top dot y. So this maneuver here, does this make sense to you? Like, that should be fairly simple.
Yeah, you just flipped it.
We just flipped the y-axis, kept the x-axis the same. So that's a simple mirror. So now, in theory, if we haven't buggered up any of the maths,
Right. Yeah, I don't do anything with that. Okay.
Yeah, because I mean, you can arrange this in many different ways, but this is how we arranged it. And now, lo and behold, we're actually dividing by zoom, so I can't zoom in on it too much. Now you'll note it's got a bit smaller, in fact, because now rather than, like, it's got smaller by a factor of 1 divided by, what, square root of 2 or something. Just because that's how the maths turns out. But you'll notice that the angle is like smaller. And if I do this trick where I like pause it and say 150, why not 160? And it gets smaller, and if I'm like, why not 120? Like, this is going to be a big fat arrow like that. So that's one way you could do it with angles that also uses basis vectors.
Yeah, I mean, I don't. Yeah, this is good for future me, who's hopefully gonna produce the fortitude to go through this again. But I kind of, while you were doing that, I kind of just put it in a different method because.
Oh, that's fine. And so what you could do is you could pass the angle in as a parameter. It's like, I want my arrow to be this big. It's probably going to be like 180 plus angle or minus angle.
Right.
Or something like that. So you just be like, I want a 10-degree arrowhead and it's really pointy. It's like, I want a 90-degree arrowhead and it's like a flat line. But one reason that you might want to do this is, if you look at this code, these are the expensive methods. Like, we're doing a cosine and a sine. So, trigonometry is fairly slow, relatively speaking. But you'll also notice that these are like static or constant. We can take these out and just stick them out here and be like, static, read only. Like, we don't actually have to calculate those every single time we run this method. And it still works. And that's one reason why...
Only if you... But that's only if you don't want a variable angle.
Yeah, this is true. But this is one reason why you do like the basis vector trick. That's because doing the basis vector trick, this is just a bunch of additions and multiplies. It's relatively inexpensive. Whereas this is more expensive. And if we had done this the other way, where we're like, all right, give me the normal, then let's transform 2D or create rotation 160 or whatever, and then dot transform the vector n, like new n. If we'd done it that way, or something along those lines, then we're having to do a lot more maths, because we've got to, if you go into create rotation, we're doing the same thing. We're like making a rotation thing, then we like spamming that out to a whole matrix, and then we're taking that and we're doing a transform on it. So we're actually doing a whole bunch more maths that we have to do every time. But if we can straight up use the basis vectors, we're in a much better position. Now, that being said, this transform 2D stuff is very similar to what we're doing. So if I can recall correctly, I believe that if you look at this section here, this should look really similar. I'll copy that out. So this is the transform. Let's comment it. So we have our Vx. So this is our vector that's incoming, and then we have here's our top x times n. Let's see. Yeah. So this is split out differently. In fact, it's going to the x and the y, whereas this is doing it all in one step. So still, we've got our x. So this is top.x, and we're taking it there and we're multiplying it by this. So 1, 1 and 1, 2, that's one basis vector. So these two elements here is equivalent to n. And then we've got our y, so this is equivalent to top y, and this m21 and this m22, that's equivalent to this basis vector. And then finally we have this translation step, so that plus x plus y is equivalent to this, adding this end to it as well. So do you vaguely remember what that was about from when we did that?
Yeah, that's the one where it's like you've got the matrix of the top, but then you're taking the two bottom storage areas. Like you're not using the third dimension, but you're storing the vector in it, the x and the y.
Yeah, so that's our augmented 2x2 matrix from
Right.
that time. So this we're doing the same thing, just in a slightly different way, really, as what we did here. We're taking, we're applying basis vectors to get a new coordinate system to do a rotation or some other operation that is linear, and then we're doing an affine transformation because we're also adding a translation step. So let's leave that all as is for now. I'll fiddle with that later. Okay, let's call it.
All right.
All right, and